I wanted to talk to you a little bit about scientific notation. And just to start off with, scientific notation, it gets used in a lot of places. I will say where it tends to be most useful is it's a standard type of notation that we use for very large or very, very small numbers. One of the ones that I like to go to when we're looking for examples is something called Avogadro's number. And you're gonna run into Avogadro's number if you start doing chemistry for very long, or if you've been doing chemistry, you might be familiar with this one. This one is approximately 6.022 times 10 to the 23rd. Now it's like, oh, wow, sure, why not? And you don't really get a sense of how big this number is until we actually write this out in decimalized notation. So this is the scientific notation, and with scientific notation we always have one non-zero digit in front of this decimal point, and essentially we've got a power of 10 that tells us where we have our decimal point. Here, this is going to be a very large number. So I would, behind the 6, my decimal point is actually going to be 23 spaces further to the right. So when I write this out, this is going to be 6.1, 2, 3, 4, 5. Oops. Actually, I'm going to regroup this just a little bit. 4, 5, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, and I messed up my decimal place somewhere, but I think. Let's see. So I've got 3, 6, 9, 12, 15, 18, 21, 22, 23. Yeah, actually that's it. That's about correct. So this would be something along the lines of, let's see here, hundreds, thousands, millions, billions, trillions, quadrillion, millions, billions, trillions, quadrillions, quintillions. So this is 602 sextillion, 200 quintillion. That's a very big number. And you could probably see where that would get really awkward to work with. Just as easily if I were working with things that were some numbers that were also very small, like say the charge of an electron. A charge of an electron is 1.602 times 10 to the negative 19th Coulomb. So it's like, you don't really get a sense for how small this is, but this is also the charge of a single electron. Well, here, instead of, because this is negative, this basically says that my decimal point is 19 spaces further to the left. So what I would do is I would start with 1, 6, 7. But so now I'd move this decimal place and start moving it out. Say, okay, that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19, and there's my decimal point. So this is literally how small the charge of an electron is. This is a very, very small number, and this would be really awkward to try to plug into a calculator, mostly because your calculators would only have this many decimal places that you could plug in. So here's what we're going to do. Whenever you're doing some calculations with your scientific notation, here is how we're going to break this out. You're going to set it up, and you're going to multiply or divide as you need it, the decimal numbers, and then you're going to do the same thing with the power of 10. Now this is usually the one place where where it's okay to end up with negative exponents. The last thing that you're going to end up doing is you're going to adjust your decimal point and your power of 10 if needed. And I'll show you what that means. So let's start off with, I'll start off with a fairly simple example. Now, we're not going to need any kind of adjustment in this one at the end. So let's show you what this is going to look like. Say I've got something like 3 times 10 to the 8th. And then let's multiply this by, I'll multiply this by 2 times 10 to the minus 3rd power. Here, when I do this, I like to say we're grouping things. We're going to regroup our constants. So I've got my 3 times my 2, and then I'll put my powers of 10. So I've got my 10 to the 8th times my 10 to the negative 3rd. So this is just going to be 6. So 3 times 2 is 6. And I've got my power of 10. Here, I just need to add together my exponents. So I've got 8 plus a negative 3 is going to be a 5. And we're done. Now, where it gets interesting is where we might need to adjust our decimal point here. So let's say I've got something like 5 times 10 to the, I'll do 10 to the negative 6th. And I'm going to multiply that by 7 times 10 to the, how about I do 12th? Okay, now when I do this, I'm going to still regroup. I've got 5 times 7, and then I've got 10 to the negative 6 times 10 to the 12th. So this is 35 times 10 to the 6th power. Now, we only want one non-zero digit in front of the decimal point. So, and our decimal point is essentially right after this whole number, right here. So what I can essentially do, what I'm going to do is I'm going to, and my shorthand here is if I'm moving my decimal place to the left, I will just move that decimal place and I'll add 1 or however many places to our exponent. The reasoning behind that is this. We're essentially doing, that's going to be 35 times that 10 to the 6th. This is really 3.5 times 10 to the 1st, and then times our 10 to the 6th. And sure enough, that's where that decimal point is, where this extra power is coming from. But the shorthand is, if I'm moving this to the left, I'm adding 1 here. So that's going to be 3.5 times 10 to the 7th. Okay, what about division? Let's take a look at what division looks like. When we're dividing, we're going to divide just like we normally would. So we've got something like, I'm going to do something here where I've got something like 1.2 times 10 to the 10 to the third, and I'm going to divide this by, say, 4 times 10 to the negative, let's do negative 7th. So what's happening here is I'm doing 1.2 over 4, and this is going to be times our 10 to the third over 10 to the negative 7th. Now here, we're only using our quotient rule for the positives. So here, so on my power of 10, this is going to be 10 to the 3 minus the negative 7 is going to be 10 to the 10th. On these, we're just going to do this straight up division. 1.2 divided by 4 is going to be 0.3. Now here, when I look at this, I also need to adjust my power of 10. Only this time, this is a smaller number. I'm going to move my decimal place one place to the right. So when I move my decimal right, we're going to subtract 1 from our power. So this is going to be 3 times 10 to the 9th. Now, once again, the reasoning behind that is I could fairly easily write this out this way. So times 10 to the 10th, this would be 3 times 10 to the negative 1, and then times that 10 to the 10th. And it's pretty easy to see why I'm subtracting 1. So that's 3 times 10 to the 9th. You do have to watch your signs when it comes to your powers, especially. Remember what happens. I'll do another example here where it's where we might have something more interesting happening with our powers. I'm going to go back to some multiplication since a lot of folks seem to be happier with that. Let's say I've got 4.1 times 10 to the third, and I'm going to multiply this by, say, 5 times 10 to the negative 16th. So when I do this, I'm going to end up with, what is that going to be? 20.5 times 10 to the 13th. And my thought process here, I'm just moving fast. I've got 4.1 times 5, and that's going to be our 20.5. And then we've got our 10 to the third times 10 to the negative 16th. That's our 10 to the, negative 13th. Knew I was missing something there. Now, what happens when I add 1 to this? This is a negative number. When I add 1, so this becomes 2.05, this is going to be times 10 to the negative 12. Because a negative plus a positive, we subtract the numbers and keep the sign of our bigger power, or our larger number. Alrighty, that's all I've got for right now. I will see you in the next meeting.